Hey everyone, can you guys hear me all right? Yeah? Okay, yeah, it seems like at least half the people can hear. No, I'm just kidding. Hey, so I'm Luke Wood, and this is Have You Ever Seen an Astronaut Riding a Horse? Image generation theory and application. Image generation's a topic I'm really excited about. I've been working with it since 2016 or so, as I'll discuss in a minute here, but yeah, this talk covers the little history of generative image models, modern image generation models, and more specifically, the architecture of the popular Stable Diffusion model. And also at the end, I'll show you a few different ways to use that model. Yeah, just how you can get started using it in the quickest way possible. And hopefully when you leave, you'll understand not only how it works, but also, ways it may go in the future, generative image modeling, and ways you can use it in your applications. So for the technical parts of this presentation, I'm going to assume that you know a little machine learning, but not generative modeling. Yeah, just basically how a neural network can approximate some sort of function and maybe what a vector is and these sorts of things. So, yeah. So I'm going to start off with a little anecdote instead of just jumping into it. So last week I was in Bruges, and I wanted to get a picture by the famous waterway, and I did. So you can see me here. But you might notice there's like some boats in the background, and it's kind of ugly to have these boats in there. And so with this talk coming up next, like the next week at the time, I thought to myself, well, what if I try to use a generative model to in-paint these pieces of the picture? So I did that there, and so basically all you do is tell the model, highlight the boat pixels, and then tell it what to fill in. So I gave it the prompt. I think it was a man sitting by the waterway in Bruges. And so yeah, I did that just out of the box, which is like pretty cool. This one I used DALL-E 2, which is not open source, but you can do the same thing with Stable Diffusion or anything else. And then I realized I didn't have any pictures of the landscape itself, and the weather was no longer good. It was kind of rainy, and so I was like, oh man, I have no pictures of the waterway. So then I was like, what if I just take myself out too? So then I had this picture where I'm not in it. And then I was already kind of making all these wacky pictures of that. It's like half of this isn't even the real picture anymore, And then I was like, what if I just like put a unicorn in there or something like that? And so, yeah, it's pretty cool what these models can do. This was literally just, this is not a real picture of a unicorn photoshopped over it. This is just a generated unicorn from the prompt, a unicorn standing by the waterway in Bruges. And, it's from this original picture here. So it's pretty cool what you can do with this. So yeah, there's like a wide variety of use cases for these models, as you can see from just the intro slide and here. Just really quickly before we carry on, the slides are available online. If you have your phone, you should use the PDF version, which is linked right here. If you're on your desktop, use this one. Unfortunately, I couldn't get the web version to work on phones. I don't know why. It just was literally making my Safari browser crash. Maybe it works on Android, but the slides are definitely safe in PDF form for phones. And then the code for the demos is also available online. Yeah. So just really quickly, a little bit about me. I'm from San Diego, so traveled a little ways to get here. I work on the Keras team at Google. I've been spending the last year or so on KerasCV, which hosts a version of StableDiffusion, which is one of the very mainstream image generative models. And I'm also pursuing my doctorate at UC San Diego. I've been working with generative image modeling since 2016 off and on. I've been doing ML since 2015. I started with a little undergrad research-ish group that did ML, and one day we were working with generative image models and we couldn't figure out what was going on and why it wasn't working, and somebody sent this angry looking cat doll in our group chat, and we all started changing our GitHub avatars to that. And so just keep an eye out for these later in the talk. I put them as one of the things to generate here and there. So yeah, it's kind of fun. Yeah, and recently I've been working a lot with StableDiffusion and KerasCV. So why should you care about generative image modeling? Historically, the real answer was probably that unless you found it really interesting and cool, you probably shouldn't have cared that much. Like, it wasn't very useful. Like, you could generate fake shoes. These aren't really real shoe pictures, but what are you, what are you going to do with that? It's not particularly interesting. You could learn the latent space of a data set, which we'll talk a little bit more on later. But the top row are real handwritten digits. The bottom row are not real handwritten digits. They're generated based on the latent representations of the above one, which is basically a very compressed format. We will discuss this quite a bit in a bit. And lastly, you could do some more interesting things like generate deep fake videos. On the left is a real video of Obama talking, and the right is a generated synthesized video of Obama talking. So you really can't tell the difference, but so you could make people look like they said things they didn't and stuff like that. But it's all quite interesting, but nothing that useful really. It was a little too difficult to control the outputs of the models to do interesting things. You had to hand curate them, and all in all, you needed quite a few samples to generate new samples to train the models. And it really wasn't that interesting. And that was until about 6 months ago when OpenAI launched DALL-E 2, which is a really, really popular and very powerful image generative model. It was like the first, I'd say, like mainstream text to image model. There were some older ones before that, but they were not that effective, not that powerful. And you can see here, like, this was kind of the first prompt that they launched it with, an astronaut riding a horse in a photorealistic style. And like, this is just like incredible. I mean, look at this. It's really amazing. I mean, you really can't tell that this is a synthesized image. I mean, it just looks like an astronaut riding a horse. And so this was really cool, but the model was still closed source. Nobody could really use it. And that's kind of a shame. They do have an API that you can use it behind, especially now they've opened it up a little bit more. But then very recently, I think just about maybe a month ago, StableDiffusion was launched. And this is a fully open source text to image model released by a startup called Stability AI. It's 100% open source. It's generously licensed, and it works basically very similar to DALL-E 2. It's actually more similar to another model called ImageGen, which is also not open source, but it gets the same thing done. So you can see here, you give it a prompt like Paradise Cosmic Beach, and StableDiffusion outputs something like this, right? Like an image. So now just before we carry on, I'm just going to show a few of these just to give you an idea of what some of the outputs you can get. A gentleman otter in a 19th century portrait style. It's pretty cool. A cute magical flying dog. Fantasy art drawn by Disney concept artists. Like, I mean, this is amazing. Like, these are not real pictures. These are just generated from scratch, just based on the prompt. Pencil sketch of robots playing poker. I mean, you can even see the poker chips here. Like, it's pretty good. And then last one is multicolor hyperspace. I don't even really know what to say of it, but it does look like a multicolor hyperspace to me. So, yeah, that's not all. You can also do image-to-image workflows guided by text. And so what that might look like is, you start with an image like the one that was generated before, and you erase part of it, and you tell it what to put in there. So like a pirate ship, and it can do that. So this is exactly what I did with these images. I erased this part of the image, the boats, and you can do that in an automated fashion too if you use a segmentation model. But and I told it man sitting by the river in Bruges, or just the river in Bruges, or a unicorn sitting by the river in Bruges. That's also not all. You can also do as you saw in my intro, you can do in painting, but you can also do out painting. And so you may be familiar with this famous painting, "Girl with a Pearl Earring," by I actually can't remember who painted this right now off the top of my head. That's not good, but So anyways, if you wanted to imagine what's outside of the frame in this picture and preserve the style, you can do that with the model. I mean, this is the synthesized by, I believe, DALL-E 2, an outpainting of this image. And you can also do other things like generate variations of images. So, seeded with the original, you can generate all of these. None of these are real paintings. They're just synthesized based on the input. This was done using StableDiffusion, which is the model we'll talk more about today. But yeah, the point is there's a lot you can do with this. And so let's just take a really quick step back now, and we'll start actually going through the details of how this works and how you can get started using this yourself in your own products and things like that. So, really quickly, does anyone have any questions about anything we've gone over here? Or yeah?
Will the same prompt result in the same picture every time?
So we can come back with that. He asked, will the same prompt result in the same picture every single time? And we can revisit that in a little bit here. Yeah. So before we continue on to the actual generation, I want to introduce some concepts here. The first is the latent representation, and the second is continuity. To get started talking about these, let's revisit an old type of model. It's called the autoencoder. So this is a traditional machine learning model, or I guess traditional is a funny phrasing, but it's an older machine learning model where instead of, like in most machine learning models, where you have some sort of input features and you're trying to predict some sort of different output features, such as the contents of the image in a classification problem, whether it's a cat or a dog or a tree, the input and output are actually identical. And there's two neural networks here, a encoder and a decoder. And you might think, okay, well, isn't this just the identity pass-through function or something like that? And the answer is yes, but there's a catch, and in between them, there's a compressed representation, also called a latent representation. And so the input images, especially, or at least in this case, are 32 by 32, I believe, or maybe they're 26 by 26, I can't remember. But the latent representation here is only, what is this, like 10 numbers, right? So you can see this is a very compressed representation. Whatever, so it's like 32 squared down to like 10 numbers. So this is called a latent representation. It's this compressed space where you can get images into, and then you take the latent representation, you feed it to the decoder, and it attempts to reconstruct the input, and you run backprop through the entire thing. And the goal of autoencoders is to get a really coherently organized and logical representation of your data set. A little fun history, autoencoders travel back to 1987, which is like pretty early in terms of ML. There was no large-scale like data sets. The goal was to run backprop without a teacher, and the teacher is like an annotated data set. So the goal was to gather information about an unlabeled data set, which is now something that's becoming very popularized in the space of contrastive and semi-supervised learning. But back then they tried to do it. Unfortunately, there weren't really any good results back then as far as like visual things, like we just had even for the handwritten digit set, but they came up with the idea back then. But if you flash forward to the 2010s with things like TensorFlow and GPUs and large data sets, autoencoders really took off as like an area of interest for a lot of researchers and students and academics. So yeah, I mean, the most important thing you should take away from this little spiel is that autoencoders are a form of compression. They take an image down to a smaller representation where each number in that representation is very meaningful. And then they can re-expand them to the original. There actually was, some discussion around shipping autoencoders to things like a web browser as like a very strong form of compression. But there's some caveats with autoencoders. One is they're very data specific. You can't generalize to things outside of your original data distribution. So to train a general case autoencoder for the entire corpus of the internet and use it on everyone's device, not very realistic. They're also lossy. So and unlike JPEG or other compression algorithms, there's no real predicting how lossy the autoencoders will be for a given image. Like you can't really control that. And so they're basically never used in practical applications, at least according to the Keras blog in 2016. That's not really true today. But yeah, I mean, they're used occasionally. They were used in some like research works, but they weren't very useful until recently. So what happens in between the real samples of your training distribution? So what you're looking at here is, here's the code to generate this plot, but the really important thing is these are all the handwritten digits and their corresponding colors. and this is a 2D autoencoded space. So you can see that they're actually somewhat coherently clustered, especially considering that the model had no concept of a label. It was just training on unlabeled data, and you could actually write a decent classifier from this. But what happens in between these points? So what happens if you take this 2D coordinate, so it's 2, -1, I guess, on this plot or whatever, and you feed it to the decoder? What does the autoencoder come up with? And the real answer is it interpolates between the points around it, really. And you can generate new images. So you can see here, this is a 2D grid where each point is run through the decoder and expanded into a resulting image. And you can see this is kind of how autoencoder spaces look internally. Unfortunately, you can't really visualize spaces super well that are above 2 dimensions, just because that's how we perceive information. But the real point I want to introduce here is that this space is continuous, and there's a lot of things in between here. And so when you're generating a new image, you're not just entirely making it up, it's really an interpolation of all of the training data that was fed into it. So even here, maybe this 0 was in the training set, who knows, or something very close to it. But there's definitely points in here that were not in the training set, and everything in here looks like a coherently handwritten digit. So yeah, the point is these latent spaces are continuous. You can sample from within them and re-expand them. This is a really, really, really key concept for understanding image generation. So now just to show this off, using a text-to-image model, we generated some kind of fun GIFs of what's called a latent walk, which is you walk through the latent space in small increments and run the latent representation samples from each point through the decoder, and you just look at what's generated. It's kind of a form of seeing how coherently organized your latent space is. And so you can interpolate between the different points in the latent space. So we actually use 2 prompts using a text-to-image model to do these. But so here you can see a panda transform into a plane over time in a latent walk, and it's kind of fun. So we have a couple of these for you. But yeah, this is just the latent representation of the prompt. I believe it was panda and plane. There might have been a little more information, like a stained glass of a panda, and then some sort of artistic style for the airplane, but the point stands. And then we have a dog to a bowl of fruit. So all these points are, somewhere in between there, and I guess that for whatever reason, somewhere in the latent representation between dog and bowl of fruit, it's picture of dog, picture of fruit, because you'll see the picture frame pop up in both of these, which is kind of interesting. But yeah, and then we have a kind of interesting plot here where you can see the same thing, right? Somewhere in the latent representation, there's the dog in the picture frame. I guess that if you mix 50% dog with a pencil sketch of a skyscraper, you get some sort of beer-looking thing. I don't know, but yeah, the point is that there's coherently organized continuity in these latent spaces, and this is a random walk around the concept of a cow by a windmill. So, yeah. A really quick aside before we move on from autoencoders and continuity is you'll see the word variational autoencoder used a lot. All you have to know is that it's basically an autoencoder with one extra operation that is literally written right here. It's pretty simple. It's done to force stronger continuity, basically. But if you see variational autoencoder, you can think of it just as an autoencoder here. Congratulations. And you can see where this fits in here. So here's the architecture of a text-to-image model at inference time. And this decoder right here is actually the decoding portion of a autoencoder, a variational autoencoder specifically. Don't worry too much about the rest of this for now. We'll get there in a minute. But the point is you somehow go from this, an astronaut riding a horse, to the latent representation learned by the encoder piece of this variational autoencoder, and then feed that to the decoder. The actual training process has a little more details in it, but if you just want to use the model, you can really only worry about these pieces for now. So, yeah. So next, we're going to talk about diffusion models. And these are another critical piece in understanding stable diffusion, hence the name StableDiffusion. But they were invented in 2020 or so, and they were the state of the art in generating images for basically since their inception. Before that, it was the generative adversarial network, which was very hard to get to behave and very hard to train. Diffusion models are a lot easier to understand, a lot easier to use, and a lot easier to train. So what is a diffusion model? So the process of diffusion is continuously adding noise to an image until you can't see the image. So you can see here the forward diffusion process and reverse diffusion process, right? So it's adding noise to the input image to make it noisier and noisier, and then the reverse is removing noise from the image. And you can see the same thing here. So you can see adding noise to this dog. You can't really see the details anymore, but you sort of can, and then reversing on the bottom. And so what you do in a diffusion model is you actually train the neural network to undo diffusion. And you train it on all of these time steps. So this would be a training batch to your diffusion model, the top half. And the predictions that you'd be targeting would be the things on the bottom half, or I believe these are actually the outputs of a diffusion model. But the training target, I guess, would be the previous one to it, right? So the idea is to continuously remove noise from an image until it looks like a completely denoised image. And so if you just keep pushing this to the point of pure noise, you basically force the model to come up with something that fits your training distribution, right? So you can a helpful way to think of this is to sort of frame it like the super resolution problem that you may have seen around or be familiar with. You start with a low resolution image right here, and you remove a little noise and make it a higher resolution image. So you can see here, if you really squint, I guess, that the edges are a little sharper and the text looks a little bit better. And so the goal is to make the image look better. But so what if you kind of push this to the limit and you just keep on, you start from pure noise like you do here. Then you basically just force the model to come up with details that aren't actually there. It's just pure noise, but it looks like something that was present in the training distribution. So yeah, I mean, if you push this idea to the limit, you can generate new images. So these flowers are not real flowers. They just were generated using a diffusion process started from pure noise. So yeah, those have been around since 2020. You can read a little bit more about them on Keras.io. So just a really quick note before we move on from diffusion models, like we did with variational autoencoders, a latent diffusion model is what is actually used in the stable diffusion model. And this is basically just like a diffusion model, except it operates on the latent representation learned by a variational autoencoder. And so this is done for efficiency because it is a lot faster to perform denoising on noise in a 64 by 64 by 3 space or whatever than a 512 by 512 by 3 space. Or so you basically compress using a variational autoencoder, and then you perform diffusion on the compressed representation. That's the only difference of a latent diffusion model. The architecture used is called a UNet. You can look it up. We're not going to cover it other than the fact that it's a common architecture used for diffusion models. Yeah. So yeah, now you know about half of how stable diffusion works. You can see over here. Yeah, anything to the right, you know. And so now you also know why there's this loop here, right? So you have this latent representation that you're targeting, the variational autoencoder's latent representation when you train your diffusion model, and you loop it. So you feed it through the diffusion model over and over again to continue denoising it. And so that model gets used 50 times or so during inference, most of the time 50 times. And that is where almost all of the computation goes during inference. Really quickly, just before we move on. So yeah, we're going to really quickly cover the text encoder, but this is not a talk on natural language processing. So we're just going to show it's like a really high level overview of how it works. You need to know the clip model and only some pieces of the clip model, really. So clip is algorithm introduced by OpenAI to create a joint representation for images and text. And the way that it was trained is you have, well, each of these is a transformer model, which all you have to know is a neural network that maps from either text to a latent representation or an image to a latent representation. And you can see that here. So you have Pepper the Aussie pup, and here's a picture of Pepper the Aussie pup. And you take these pairs, and you take a batch, so you can see it's like stacked right here, right? And you get latent representations. So T1 is the latent representation of the text Pepper the Aussie pup, and I1 is the latent representation of Pepper the Aussie pup going through the image encoder. And they use a loss function that encourages similarity between these two. So I1 and T1 should be similar, and then I1 and T2 should not be similar. So you train it to have positive and negative pairs, if that it makes sense. And so you can get a joint representation for images and text by doing this. And they train this on many, many, many text-image pairs. So that's basically all you need to know about CLIP, is that it's a joint representation from text to image. And it's pre-trained, actually. We don't train this in the use of Stable Diffusion. All we do is take the text encoder, freeze it, and just use it. Right? So now we have a text encoder that goes from text to something that resembles a latent space of images, right? So this T1 looks like the I1 representation of Pepper the Aussie pup. Yeah. So you can read more about CLIP on the OpenAI blog post. By the way, anything that's blue in the presentation is actually a hyperlink. So if you open the PDF or the slides online, you can click on those. Yeah, but so now you know almost everything. So you have an astronaut riding a horse, goes through our CLIP text encoder, and this is encoded to a vector. And then, by the way, this is just a random number generator that produces Gaussian noise because diffusion models operate on noise. And then those go to the diffusion model, get looped through 50 times until it looks like something, and then go to the astronaut. Now you might notice there's something missing. How do you feed this like text representation and the random number generated Gaussian noise to the diffusion model? And that is the final piece of what makes these models work, and that is called conditioning. So conditioning is a classical deep learning technique that is used to force a correlation between two vectors in a deep learning algorithm. We're not going to go too far into the math of how it works, but you essentially just concatenate the text representation to the latent noise. So the latent noise is 64 by 64 by 3. That is the case because the latent representation of the learned by the autoencoder is of that dimension, I believe. And then you concatenate that with the text embeddings, which are 64 by 64 by 1, to get a 64 by 64 by 4 vector. And when you train your noise or your denoising model, the UNet is not quite like a standard diffusion model where it operates only on noise. It also operates on text to force a relationship between the text embedding and the denoised outputs. So during training, you can imagine that the noise, the text embeddings, are concatenated onto the noisy information. And when you compute your loss at the end, the images will always be paired with a text embedding. So you can force a relationship between images and text when you train it. And you just feed this to every step of the denoising process, the raw text encoding, and eventually you do end up with an image generator that can actually be controlled. Yeah, so that's the model. So it's not magic like it might seem from the demos and such. It's just a lot of data and a lot of independently trained components, really, because the variational autoencoder you can just train on a huge corpus of images. The text encoder, you just train on a huge data set of annotated text and images. And then the diffusion model, again, you train it with these two frozen on a massive data set of text and text-image pairs. And here's the GIF of the training that you saw in the beginning that might have seemed a little overwhelming at the time. But you can see here, all this is so this is pixel space, right? So this is an image, X. It goes through the encoder. It gets its latent representation from the variational autoencoder. It goes through diffusion, which, remember, is the process of adding noise onto the image. Then you get a latent noisy representation. You concatenate the text from this frozen text encoder that we don't train right here. And then you go through the denoising process based on each noisy step here. And then you run it back through the decoder to get the predictions, and you compute the loss based on that. And that's how you train this model. So that's really all. That's how Stable Diffusion works. That's how it was trained. It's very, it's not magic. It's just a lot of data. So now the exciting part. Now the technical details are kind of, or the deep mathy parts are all wrapped up. So how do you use it? So text to image generation is the first one. And so you take a prompt, you feed it through your frozen encoder, you get your text embeddings, you concatenate them to the Gaussian noise in the text conditioned latent unit, and you feed it through however many times, usually 50 or so, and you run it through the decoder, and now you have an astronaut riding a horse. Yeah, there it is. I just realized this wasn't full screen the whole time. Oh, okay. Yeah, and so here's the code to do that in KerasCV. It's 8-9 lines of code, and this is a very performant pipeline too. This takes 3 or 4 seconds to generate, 4 new images of whatever you want, right? Teddy bears conducting machine learning research, or an astronaut riding a horse, or anything you want. And then, so we'll go through a demo of this in a little bit here. But then also, right, what about variation generation? You might remember the pictures of the girl wearing the pearl earrings and how we got all the generations. So remember in Clip, there's also this image encoder that has the same latent representation of the text encoder. So you don't even need to retrain another model to generate variations. You just switch the image and text encoder. They have the same latent representation, and you just switch it out. And you use that instead of a prompt. It's really that easy. So here's Van Gogh's Starry Night. And you feed it through the clip encoder, and you get these images out. And these are new images, not present anywhere else. They're entirely imagined, you might say. Pretty cool. One last use that I would like to talk about is textual inversion. This is like a pretty new technique. And by the way, remember, all of this has happened in 6 months, right? And so like a lot of these new use cases, like variation generation, textual inversion, all these things, these are all like a month or two old as far as Stable Diffusion is concerned. Like this is a really fast moving field, which is really cool. But so you can imagine how far this is going to go in the next couple years. But so textual inversion is the concept of teaching a new concept to Stable Diffusion. So what if you have something really specific, like my weird GitHub cat avatar, right, or something like that? You can actually teach the text encoder a new concept. So we invent a new phrase like S star or something like that. It could be named anything, right? But just know that it's a new word in the vocabulary of the clip model. And you can teach it what this is based on these input samples, and get it to generate these things. So like an app icon of S star, like this is amazing. This really does look like an app icon, or Elmo sitting in the same pose as S star. It really does look like this. And that's just really cool to me. But and the process of doing that is actually quite simple. So step 1, you collect 3 to 5 images of your object. Step 2, and there's the code to do so. This is all also on the GitHub slides, and there will be a Keras.io tutorial on this very soon. It's not quite ready to be published widely, but there will be soon. You add a special token to your model's vocabulary. You create a data set based on that, and so you can see here we have like a new token, which is just any special name, and this is just Python code, right? You just take templates and a photo of blah, 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 a rendering of blah, 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 a cropped photo of, and you generate prompts that are very generic and just force the model to learn the concept of whatever your new concept is. And then you fine tune only the text encoder, which is like the clip model. And you just train it on your new data set. And so you can get things like a photo of, whatever your special name is, wearing a top hat, or an app icon of special name. I think this one in particular really captures the features. But this is a very specific concept, right? Like this is an obscure type of cat doll we found on the internet, right? Like this is very, very specific. And so yeah, this is really powerful. I would expect to see more of this used around in the future, but again, the space is pretty new, so we don't even have our tutorial ready on it yet. But yeah, so a quick demo. I'm gonna go through a Colab or a Jupyter Notebook, and you can follow along on Colab if you click on that link linked in the slides. I lost my connection to my Colab notebook, but one moment here. But yeah, you can follow along if you click on that link. Okay, that's why. So let's start at the top. So first of all, yeah, you just have to install these packages. There's a couple linked in the slides. There's a couple cells to do that for you. You create the model down here using the KerasCV package, which has a version of StableDiffusion, and then you can run just text to image like this. Does anyone have a prompt idea? You could be as wacky as you want, right? All right. Let's do.
Scuba playing a bass.
Who?
Scuba playing a bass.
Oh, that's a cool one. Let's see. So it'll take a couple seconds here. The first, it's not connected. That would make sense why it's not running. Okay. Let's see. We might have to refresh the page. All right. So let's see. Hopefully this runs quickly here. But just in case, you can follow along as well on your laptop in a couple minutes. I'll have a link to the slides and GitHub repo again at the end of the talk if you want to take a picture and save a link to it or anything like that. But yeah, it looks like it's taken a minute here to load. The first time you run inference, it has to trace the TensorFlow graph, which can take a minute or so, but the follow-up ones only take a second or two. I guess while we give this some time to run, does anyone have any questions in the meantime? Yeah.
There seemed to be an import error at the top.
So this is that's a installation error. This is written for Colab, and I'm running this on just like a personal VM that is already pre-configured. Yeah, no, thank you. that'd be problematic for sure.
Do you make use of the local GPU cores, or?
Yes.
Okay.
This is all. Oh yeah, I should make it really clear. This is
Maybe print the type, which percentage and type.
the
Can you print the time of the computation?
Oh, okay. Wait, okay, here we go. So yeah, you can kind of see here it does a pretty good job with the scuba diver playing the bass. It's not amazing, but wait. You can play with it a couple times. And to answer the question earlier, by the way, that you had actually, just to remember, now that I remember, you can actually give it a random seed. So does it produce the same thing for every prompt? No, but it does if you use the same Gaussian noise. So if you seed it with like 1, 2, 3 or something like that, you will get the same thing. So it just depends on the Gaussian noise. But yeah, so it gets the concept of scuba diver. Maybe it doesn't get the concept of bass. Maybe we should try guitar. So again, you know, it only can generate things reflected in the training distribution. So I guess, yeah, okay, there we go. That's so funny. But yeah, it's like guitar was more represented in the training distribution than bass was. An unfortunate fact, but yeah.
You mentioned before when generating variations
Mm-hmm.
that you swapped out the algorithm generating the like latent representation
Yes.
text with something else.
Okay, yes.
What were you switching it out with?
So now that, yeah, the demo is probably, I'm going to actually start, before we revisit that really quickly, the next piece of the demo, which is just a latent walk. Oh, wait, it's already run, actually. So you might remember those latent walk. I'll come back to this, actually. So yeah, to answer your question, you might remember clip is the joint embedding of an image and text representation. So you take the image encoder from clip, and that's why you don't have to retrain anything, is these already share a latent representation. Does that answer the question? Yeah, cool.
How do you end up with a variation from that?
So,
Adjacent cell or something?
so you add Gaussian noise to it again. So this is actually used as the text embedding, quote unquote, in the denoising process. So this is the conditioning vector, but then the latent noise is concatenated to that, or the Gaussian noise is concatenated to that. So then when you actually run the process, it generates images that are similar to this, as if this were a text prompt. Yeah. Cool?
Question?
Yeah.
The initial training, it involves millions of labeled images, and it took a while to train, I guess.
500 billion. With a B.
So is it possible that I add my own couple hundreds of annotated photos, like photos of my grandma Nana, and then I ask in the text prompt, Nana playing guitar? Does it work?
I would use textual inversion for that case, which is this process here, of teaching it a new concept, and I would make your special token Nana or whatever, as long as there's no conflict in the vocabulary. And then we actually will have a tutorial on that very soon, but you also can fine-tune the model on other things. The most popular example online is somebody fine-tuned it on annotations of Pokemon. So yeah, it generates only pictures that look like Pokemon. So it's pretty funny. They give it like celebrities and stuff, and it's pretty funny. So yeah, that is the conclusion to the talk. We have, a lot of possibilities. Just remember, this field is 1 month old. Like or not 1 month old. Sorry, it's 6 months old. But the open source accessibility of this field is 1 month old, and people have already come up with a ton of amazing workflows. We also have the where'd my demo go? Here it is. Yeah, like you can walk the latent space from. So here's 2 prompts. Mysterious ruins in the snow, concept art, digital art station. Mysterious ruins in the summer, sunlight, concept art, digital art station. And this is what it comes up with. Like, this is so cool. I mean, you're just walking through that latent space between those 2 prompts. This is an interpolation. And yeah, I mean, this is amazing. So there's a lot of cool things you can do with this. Yeah, there's more workflows coming soon on Keras.io. There's a tutorial on how to generate images from text to image available. Textual inversion will be available soon. Hopefully image variations will be available very soon. But yeah, there's some other links if you want to get started running other implementations. You can do textual inversion already with Hugging Face, or image variations with Lambda Labs. They have a GitHub repo for that. And overall, yeah, thanks for coming. Here are the slides and the web link, the PDF of the slides for mobile users, and here are some links to just KerasCV, and yeah, thanks a lot.